All right, hi everyone. My name is Howard. I'm a PhD candidate at the University of Toronto. This is a recorded version of the presentation I gave at Thousand Island Meeting 2025 at Gananoque, Ontario, Canada. Today we're going to talk a little bit about flow plus a circular cylinder. So I'm calling it infinite span here. For experimentalists, you also know this as 2D cylinder, but the simulation itself is 3D. So starting with a bit of motivation, so quite often when we look at airfoil, especially at high angle of attack, because of flow separation, we get a stalling of airfoil where we basically lose a lot of the lift and also suffer from increased drag. So even on a 2D cylinder, a quote unquote relatively simple geometry, we can still see a lot of the similar phenomenon in terms of flow separation. And especially with the increase of recent interest on low to moderate Reynolds number flow, there's still definitely quite a bit of interest on basically suppressing flow separation or at least improving the aerodynamic performance on simple geometries. And our great applications for 2D cylinders are a lot of civil engineering, actually. Things like skyscrapers, if you do city modeling, quite often you have maybe like a perfect circle cylinder as a condo, but they could have different similar shape. And a great example would be offshore wind turbine farms, especially the submerged portion. So flow condition, the Reynolds number is based on the free stream velocity U infinity and the diameter of the cylinder. The current configuration, our Reynolds number is 3900. So this is known as a subcritical region. For this geometry, what we expect is a laminar separated flow, but then it transition into a turbulent. Streamwise direction is X, transverse is Y, span-wise into the page is Z. On the lower right, that's our computed domain. The cylinder is basically the tiniest white dot in the middle. And basically a cylinder is situated 25D from the boundary. We do have a width of 3D into the page. In terms of boundary conditions, so we have a uniform laminar velocity inlet. For the pressure, we're giving them a zero gradient on all patches. And this is technically an external flow, so we do have a pressure reference location here. And finally, for the front and back, we're giving it a periodic boundary condition to achieve the infinite span-like modeling. So the simulations were conducted in OpenFOAM V1912. This actually gives you a hint of when I started my master. So this is LES, Large Eddy Simulation. We are using the whale model, giving us a little bit better results closer to the wall. We've gone with a O-grid. You can see the mesh on the lower right, 6 million cells. You can cut it down if you kind of use something that resembles more of a C-grid, but then you have to deal with non-orthogonal cells. So we're kind of stuck with a more standard O-grid for now. Both spatial and temporal discretizations are second order. Y plus, maximum less than 2. In the wake, we are resolving at least 90% of the turbulence kinetic energy. So starting with a bit of validation. So what I'm showing here on the left, these are basically time average streamwise velocity profile, normalized by the free stream velocity at different locations. Current results is the blue line, and we're comparing with Lourenco, which is actually based on time resolved PIV. Overall, the comparison, especially at the wick, is quite good. Next thing we looked at was the drag and lift force. Um, so if we look at the lift coefficient, it's actually pretty interesting. So because the 2D cylinder is basically symmetric, so we do kind of see the flapping motion of it. Even the amplitude, kind of the change of it is relative. So even though this looks symmetric, this is not RANS, this is not URANS. We cannot cut the geometry into half and put a symmetry boundary condition onto it. You cannot symmetric turbulence, so you have to model the whole thing. So based on those two plots, we got some pretty interesting or useful data. So drag coefficient 1.11. This is similar to other LES study within this Reynolds number. Based on the lift coefficient, we also got a vortex shedding frequency of roughly 1.2 hertz. This is actually the wake frequency as well. This is not a non-dimensional unit, so we did not compare that directly with other studies. However, what we could do is that we can calculate the Shoho number, which in this case came out to be 0.2, and again also aligns well with other existing LES studies. This FBS, vortex shedding frequency, is actually pretty useful for us in the purpose of normalizing our results, and also we'll talk about it a little bit towards the end for separation control. So the Reynolds number is pretty low. Is this really turbulent? So what we've done is we've calculated the time average Reynolds stress contour and present on the left. And then we pick 5 locations and then place some probes and sample them over a range of time. What we were able to see is that, so we have included the energy spectrum on the right. On the upper right, that's based on the streamwise velocity. On the lower right, that's based on the transverse velocity. We also include the -5/v slope. So if we start from upper right, actually both of the plot, you actually see the major peak at 1. So the frequency already normalized based on our vortex shedding frequency. So this confirms that it is the primary energy. The second one is actually at a 2 FBS. And if we look at the red line, which is probe 1, located actually at the edge of the shear layer, we take it out and we plot it again. We actually see the footprint of or the energy of the shear layer frequency, which is roughly an order magnitude higher than our primary, or basically our wake frequency. So these are instantaneous Q criterion contours animations. On the left, I have isometric view. On the right, I have a side view. So because of the low Reynolds number and also the low frequency of the flapping, 1.2 hertz, these are actually real time or real flow time. So if we look at the leading edge here, you can see the laminar separation, but then it does transition to turbulent, and then there's quite a bit of fluctuation back and forth in terms of the span-wise direction. On the right end, we do see the flapping motions of the cylinder, and this transitions into the wake. Staying true to the name of the model, we see some very large eddies. Now, our Q criterion contours animations are cool, but quite often we do want some quantitative results. And in this case, we're using POD, otherwise known as pocket orthogonal decomposition. Historically, PODs are developed primarily for experimentalists, but there are still uses for it in numerical work. The idea is that if we take a series of snapshots, especially planar snapshots, and then feed it into an array or feed in the POD calculator, we get 3 arrays back. The snapshots are primarily 2D planar data. This is why like it's great for experimentalists where they have quite often like say PIV results. In this case, we're sampling that basically the mid span. We took 10,000 snapshots. Luckily, it did converge conveniently after 5,000, which is good. Nobody wants to do 10 million snapshots before their POD results converge. Now here on the plot on the lower left, we basically looked at or plotted out the energy for the first 100 modes. The distribution is actually quite low in the sense that if you combine the first 3 modes, it accounts for actually just under 20% of the energy. We have looked at up to 24th mode, but primarily the first 6 modes are interesting. The rest of them does kind of picks up a bit of the noise. So on the left, I have the actual mode contours, and then on the right, I have the respective power spectrum density, and I've also mapped the peak with the frequency. Now, if we dig up some of the data we looked at earlier, especially the spectrum, our power density spectrum, and also our vortex shedding or frequency, and compare it with the mode 1 and 2 peak, they're actually almost the same, basically 1.2 hertz. So this allows us to associate mode 1 and 3 with the first peak. And similarly, if we looked at mode 6, we have a peak at around 2.4 hertz. If we normalize it again with our vortex shedding frequency, that allows us to basically associate mode 5 and 6 to the second peak. We are still in the process of trying to isolate the effect of the shear layer frequency. So far, we have not been able to identify it, but we might look into combining or doing a sum of multiple modes to see if we can extract the energy. Future work. So the next step would basically be integrate a synthetic actuators for active flow control on the 2D cylinder. The goal is to see if we can reduce the drag coefficient and the separated length. This is kind of where this is kind of where the actuation frequency becomes important. The vortex shedding or the wake frequency and the shear layer frequency that we calculated or found earlier will be actuating the flow at that specific those 2 frequencies. It's telling them a bit, which is basically why we use the POD. Well, thank you for listening. If you have any questions, please feel free to reach out.